Okay, thank you for the introduction, and thanks to Professor Panigrahi for inviting me to give a talk. I know this is the last talk before lunch and everybody's hungry, so I will try to keep on time and finish whatever I want to say uh, as early as possible. So I am going to talk about the physics of optimization, introduction to quantum annealing. This is going to be an introductory level talk because I think the audience consists of different kinds, different levels of people. So I won't be talking much about in depth about the equations and everything. But in the end, I will talk a bit about how I approach this pitfalls which will happen. But let me begin by so, okay. So, by a very cheesy quote, which I'm not sure which if you have already heard in this workshop, which is by Richard Feynman. So I think Feynman was one of the first proponents of quantum computation, and he has this famous quote which says that nature isn't classical, damn it, and if you want to make a simulation of nature, you better make it quantum mechanical. And golly, it's a wonderful problem because it doesn't look so easy. And it's been 50 years, and we still haven't really completely solved the problem of quantum computation, let's be honest. So he was right that it doesn't look so easy. And he was also right in the fact that it will be easier to simulate like the very microscopic properties of nature using quantum computers because we know that at least if not, it cannot be solved classically. There are some problems which can be much easily solved with quantum mechanical simulators than the classical simulators. So how do I view quantum computing? Well, this is an analogy which I usually give in the beginning of my talks because I feel it's really nice. So let's say you want to go from a city A to city B, and you use a vehicle on road or to say train via tracks, and that is kind of classical computation. So you have traffic jams and things, and those things are kind of the problems you face in classical computation. Whereas quantum computation is actually a completely different beast altogether. So it's like traveling via air. So technically, you should be able to go from point A to point B much faster. But the problems that you're going to face are going to be a completely different class to what you have seen by traveling via road. And to be quite honest, we are in the initial stages of quantum computation. So we're like figuring out, like the Wright brothers try to figure out the problems with planes. We're trying to figure out, like, put out fires everywhere. That's what's happening. And the thing which I am interested in quantum computing are two, basically. One is to simulate quantum many-body systems, which I find quantum computing to be quite useful, and to also solve classically hard problems efficiently. And this is what I'm going to focus on this talk. I will tell you what are classically hard problems and what do I mean by efficiently. And currently, I would argue that there are like two basic classes of quantum computers. One is the analog quantum computing, which has actually physical qubits, and you actually tune the Hamiltonian itself. So that's analog, and this is best suited for simulating quantum many-body systems and also like solve classically hard problems, which you'll see later. The other one, and which is actually the end goal, I would say, is digital quantum computing, which is going to be using logical qubits, which are going to be error corrected, meaning if sudden, in fact, your classical bits which you have in a computer are technically error corrected as well. So suddenly, if some weird external noise flips the bit, you know that the bit is flipped and you correct for it. We want to do that for quantum computers as well. And the gate based is like in classical computers, you use AND or the universal gates, NAND and NOR and so on. We want to build gates like that for quantum computers where you don't really care about the Hamiltonian, but you're going to look at complete the gates and figure out what is the algorithm. So it has been realized already in small scale, I would say in IBM or Google. And I say small scale because the fidelity or basically the accuracy of the gate you require to really solve quantum problems is very, very large. So to give you an example, let's say a single 2-qubit gate, like 2-bit gate, is 99.9% accurate. But typically, for solving quantum problems, a quantum algorithm requires thousands of such gates. And if you do a naive calculation of what will happen if you apply 1,000 such gates, even if it's like 99.9% accurate, if you don't do any error correction or anything, you will find the answer you get is actually only 36.8% accurate, to put it roughly, which means that it's completely random, to be honest. It's worse than a coin toss. The probability of being correct is worse than getting ahead in a coin toss, and it's not useful. So that is why people are trying to do error correction, and we're advancing, but we are still not there yet, I would say. But now the question is, what is the backdrop for my talk? So the backdrop is, as I said, classically hard problems. And I'll start with an example, which is called the traveling salesman problem. So this is probably the most famous example of classically hard problems. There are lots of others, and the idea is you have, let's say, a list of cities, and a traveling salesman wants to visit all those cities only once and then come back to its home city. And he wants to keep the cost the lowest. The cost can be anything. It can be distance, it can be time, it can be actual cost, and so on. So then what is the optimal route to do so, to keep the cost less? And this sounds like a very simple problem, but if you think about it, maybe if you mentally can calculate it for 3, 4, maybe 5 cities, and then let's say you have 20 cities, you can calculate it maybe by a classical computer. But let's say you have hundreds of cities, then you'll quickly realize that trying to solve this in your head or even a computer is very hard. And this is not an artificial problem, because this is something which things like Amazon, Flipkart face every day. So now instead of cities, think of houses. And instead of a salesman, think about the truck that picks up your deliveries from Amazon and tries to distribute it across the city. They have to figure out what is the best path to do so, to reduce fuel costs and reduce everything. And they also have a paper out to discuss about the difficulties of doing this. And this is a modified version of this. It's called a vehicle routing problem. But I know people talk about that these are classically hard and so on and so forth. But to say something is classically hard, you need to really understand what do we mean by classical computation? What are we doing exactly? And that's why I kept this slide briefly. And the person who told us basically what we mean by classical computation is this gentleman on the right. His name is Alan Turing. So while Charles Babbage created the classical computer, Alan Turing really told us what we mean by classical computation, and we have this Turing machine. So I'm going to be very briefly describing what the Turing machine is, because I want to emphasize one particular point of it. So I'm not sure how many of the audience remember. I'm sure some of them remember, because the professors obviously. There was something which was like 25 years ago we had, or 30 years ago, we had these tapes, cassette tapes, which used to have this magnetic strip. And when we used to listen to music, they used to roll and move around. And if you can read them, and then the music, you can hear the music from that. So this Turing machine, the idea is kind of pretty similar to that. You have a tape of infinite length, which is divided into cells. Now, each cell has some object inside. It's usually a binary number, because we are talking about computers after all. And then you have a blank spaces and binary numbers. And you have a reader. You have to read what's written on the tape. And this reader can also write, so it can edit what's on the tape. But it can edit depending on what the user, some inputs of the user. But the crucial thing is this reader can only check one cell at a time. That is the most crucial part of classical computing, and it can only move one step to the left or right. And if you think about it deeply enough, everything which you do on a classical computer, if you reduce it to the very, very basics, machine language, it is basically this. And this is kind of the programming language we don't see anymore, because we have reached high-level programming language. But at the very basic level, a programming step would consist of 5 things which you have to tell the system. You have to tell the initial state of this control object, which is called, and then what is the initial value inside this tape. And you tell what, after reading it, how you change this control object and how you change the tape. And then whether you move left or right. What it does. And this is just an example of a program based on Turing machine. There's no need to go into depth, but what I'm going to tell you is what it does is that if you have a binary string like this in the tape, let's say 10110, what this program is going to do is going to go from left to right step by step, and then change all zeros to ones and ones to zeros and stop. So the thing which stands out, I hope it stands out for you here, is we are always doing things step by step, checking one by one. So that's what classical computation is all about, and that's where the classical hardness comes from. And using this definition of classical computation, this all classical computers can be modeled by classical Turing machines, mathematicians and even computer scientists, of course, came up with a classification of hard problems. which are polynomial, NP-hard, and so on and so forth. So the idea is, let's say you're given a problem which is called a decision problem. So let's say you're given a big number, and you're asking whether a particular number is a factor or not or something. So the idea is, if you want to check whether a particular number is a factor of other numbers, that is easy, that you can do in polynomial time. But if you're told to factorize the number fully, let's say, but then if you're not given the factors at all, then it is hard to find them, right? So this is the idea of this hardness of problems. If you're given a solution, it is easy to check the solution. But if you're not given a solution, whether you can find the solution in polynomial time or not, how hard is it to find the solution? So if you can find the solution in polynomial time, that's called P hardness. But if you can't, then it's called a non-deterministic polynomial type solution. It falls under NP. And among NP, there is a class of problems which are called NP complete, which can be mapped to each other in polynomial time. But one of the $1 million questions, I think, of today, dollar or pound, euros, I don't know, of today, is that whether you can find a classical algorithm which can solve a problem in this region, NP complete, in polynomial time. This is the famous P equal to NP problem, because then you can say the classical computers solve everything in polynomial time. And then there is another part which is called NP hard, which is not decision problem, which are other classes. But the idea is this all happens, that is what people thought, is because your classical computer goes through systems one by one. And the question is, can quantum algorithms be used to speed up classically NP complete problems? Because if you can show that, then you can say that, okay, we are getting some real quantum advantage. And to be quite honest, these kind of problems are mapped as quantum many-body systems on arbitrary graphs, which I'm going to come to later. But it's not all roses, because I would argue that till date, there are only two algorithms which actually work, really. And one is the Shor's factorization algorithm, which does not fall under the NP complete, by the way. It falls somewhere here, which has Shor figured out a very clever way, using interference, of course, because quantum mechanics is all about waves. So you use interference to get an exponential quantum speedup. And there's another algorithm, which is called the Grover search algorithm, which I will also discuss briefly later in this context of my work. It has been shown to have quadratic speedup, meaning if you have n complexity in classically, then you have square root of n complexity quantum mechanically. Okay. And the difficulty of finding a good algorithm is the fact that you can use quantum superposition to encode all the solutions together, but your algorithm needs to ensure that you amplify the correct part of that huge wave function. And that is hard. That is not easy, because all the problems you cannot amplify them in the same way by interference. And there's, of course, the practical problem of dephasing and decoherence, which makes you cannot keep control a quantum system for very long. And that causes all the issues. And with this backdrop, I'm going to give you a very ambitious agenda, which I'm sure I'm never going to finish in time, but we'll see how far we go. So I will talk to you about why we require ground state preparation and how we do it, and the adiabatic approach about annealing. And I will show you the oldest and the most famous annealers that is existed in the world currently, which is by a company called D-Wave. So yeah. And then what is the fundamental bottleneck in quantum annealing? What is the problem? And which will connect to then phase transitions and gap closing. And what we actually use to remove those bottlenecks, like our approach. So this is one of the approaches. There are other people that are trying other approaches as well. And of course, I will have to show you that it works. Otherwise, what's the point? And finally, some glimpse of some quantum hardware data, which completely may or may not be related to quantum annealing. Part of it is, part of it isn't. So with this agenda, let's go into the quantum world. We have been talking about classical world before. Now let's go into the quantum world. So as I told you briefly before, that NP hard problems, or NP complete, whatever you wish to call it, are going to be mapped to quantum many-body Hamiltonians, such that you map it such that the ground state will give you the solution. That is why you need to find the ground state of a quantum many-body problem. So typically, one of the classical way to do it is called classical annealing. Is you start from a reasonably high temperature state and you start cooling down slowly so that you don't generate excitations. So this is classical annealing, and you can simulate it via, for example, classical Monte Carlo algorithms, Monte Carlo metropolis or cluster or whatever it is. So that is the traditional way, I would say. Whereas the modern techniques of quantum ways which are coming about, some of them are variational algorithms, where, for example, variational quantum eigensolvers, VQE, a quantum approximate optimization algorithm, QAOA, where they try to use gate-based structures to get ground state preparation. They try to use random gates and try to kind of find the optimal configuration of gates, which gives you the ground state from a given initial state. But the one which I am going to be talking about is quantum annealing, and I'll be concentrating only mostly on the adiabatic part of quantum annealing. But there are also beyond adiabatic quantum annealing, such as counter-diabatic methods and quantum walks. And yeah, there has been a huge body of work. This is probably the oldest kind of way to do ground state preparation in quantum techniques, because solutions are guaranteed theoretically. But whether you can do it practically is a whole another question. And that is why this talk is there. If it was done practically, then maybe it would have been done 10 years ago. So a quantum annealing 101 quickly for the audience here. So the idea of quantum annealing is, let's look at this figure on the left. Quantum annealing is that you start from an initial state and you try to go to a ground state of a very complicated potential landscape. So if you think about it classically, let's say this is the potential landscape whose global ground state is somewhere here. So you start from, let's say, a state which lies in some local minima of your problem. So classically, what you would do is you would kind of use small like heating or small energy. You give some energy to the problem so that you can jump over these barriers and then reach here somehow. Okay? If you do it quantum mechanically, then obviously you're going to use the quantum mechanical tunneling. So you're going to tunnel through these barriers and reach here. And typically, this is what you really see in quantum annealing. But I kind of don't like this picture, which is sometimes presented in quantum annealing. I like to think of it in a slightly different way, which I'm sure other people also have done before, is that you start from a potential, which is a very simple potential and whose ground state is also simple to generate practically. So let's say this weird harmonic looking potential, which ground state is here. Then what you're doing in adiabatic quantum annealing is you deform this potential so slowly that your state here is always the instantaneous ground state during your deformation. And then if you're doing it slowly enough, and then you will reach the actual global ground state. The question then is how slowly, and that is given by the adiabatic theorem. Okay? And I'm not going to go in depth to the adiabatic theorem, but I'll tell you the problem of why we require how slowly, because this is not the only state available to this. This is not the only state which the system can be in. There are loads of other eigenstates which are above all these states, right? Because this is just the ground state which I'm showing. And it so turns out that if your ground state and your first excited state comes really close to one another, and if you don't do this tuning slowly enough, there can be Landau-Zener transitions to the excited state. Okay, there can be transitions. Therefore, you have to have a time scale. You have to define how slowly. And it so turns out that the best case scenario, you will see 1 by delta square in many places, but the best case scenario is actually the total annealing time. The total time you can take to deform it should be greater than or equal to 1 divided by the minimum gap between the ground state and the excited state during your annealing. Okay. So basically, this is the idea. You start from initial Hamiltonian at t equal to 0, and then you end with a problem Hamiltonian. So you're trying to find the ground state of a problem Hamiltonian. And this is how people have been trying to solve combinatorial optimization problems by mapping them into quantum Hamiltonians. Okay. So this is all well and good. And I think you can probably understand that the bottleneck is this delta, right? And before going into depth about the bottleneck, I want to show you what is the Hamiltonian, the HS, which I wrote before. What is a typical Hamiltonian which people use during quantum annealing? And that comes from this company D-Wave, and this is how their machines look from outside. They look like any big cluster from outside, but inside you can see there's lots of wires going in. So there are lots of cooling chambers and superconducting coolers, and they use something called superconducting qubits and so on. But anyway, and these white regions which you see here are actually qubits inside their machine. And these lines show that which qubits are coupled to which qubits. So it's not like all qubits are coupled to all qubits in their machine. So there are lots of nuances which you really need to understand. But the most fundamental thing which you need to know about D-Wave is what Hamiltonian is they're using. The Hamiltonian that they use is basically a transverse Ising model, but not the traditional one which you know. It's not a 1D transverse Ising model. Rather, it's a more complicated one. So this is the problem Hamiltonian, the HP. The problem Hamiltonian is just the traditional classical Ising model, but on a random graph. So this is not just 1D. It can be anything. Jij can connect any qubit to any qubit. The good thing about this is classically, this has been shown to be an NP complete. Finding the solutions to the ground state of this problem is NP complete, which means you can map other NP complete problems to this Hamiltonian. So that is why it's a good problem Hamiltonian. But you need some quantum fluctuations, right? This is just diagonal. If you write this in a computational basis state, this is a completely diagonal object. So there is no fluctuations. There's nothing to change from one state to another. So the quantum fluctuations are given by the sigma x term, which flips one spin at a time. And this is also the starting point of the. So if you look at the right-hand side figure here, at t equal to 0, the dominant term is sigma x, which is a completely local field, which means you don't start with an entangled state. So that is easy to prepare because it's all the local rotations. And then as you reduce it, you reduce this. So this is exactly taken from the D-Wave protocol, how they do it. And then you increase the strength of the problem Hamiltonian. So in the end, this basically becomes 0. And the problem Hamiltonian basically becomes 1. And what you input is actually these terms, this JIJs and HIs, to define your problem. And to define the protocol, there is some degree of control you have over the protocol. And then you'll read out computational basis states in the end. And that would give you, hopefully, the solution to your problem. But this is very constrained, actually, this Hamiltonian, as I will show you later what's the problem with this. But this is the most typical Hamiltonian which you can generate. Sorry, I'll take a sip of water. Okay. Then I told you that the bottleneck is the gap closing, right? And where do we see such gap closing happen? Quantum phase transitions. This is the place where you know that gap closes, but we are never really very particular about how the gap closes in quantum phase transition, because we typically talk about thermodynamic limits when we are condensed matter physicists. But here we have to deal with actual finite size problems. So we have to figure out how the gap closes with system size. And that is where something interesting happens in quantum phase transitions. So just like classical phase transitions, you can define orders in quantum phase transitions as well. I'm not going to go into depth of that. And first order phase transitions, typically, it's not universal, by the way, but it's typical enough that I can write in the slide here. The gap closing happens exponentially with system size. Okay. And if you look at an order parameter, because of course there's an order parameter when you have a phase transition, it will be a discontinuous jump. So, whereas your traditional Ising, transverse 1D transverse Ising model transition, the ferropara, which we all know, is actually a second order phase transition or a continuous phase transition. So there you have a continuous variation of the order parameter, and your gap actually closes polynomially with system size. Now connect this to what I said about annealing before. I said that annealing time is inversely proportional to the gap, which means that the first order phase transitions are going to be the worst enemies of quantum annealing, because if you take this inversely proportional to it, it will require an exponentially long time in system size. Now I started with saying that I want to solve NP hard problems faster, but now I'm showing you that I still require an exponentially long time to solve such NP hard problems. So what's the use? I mean, there's no point in doing quantum, right? So this is what we have to mitigate. This is the bottleneck. So typically what people can do is they can only make A smaller and smaller. So at least for some system sizes, it's really fast, but then you reach a crossover and then you just blow up. But in some special scenarios, like has been shown in this paper, and in very special models really, they have claimed that its first order phase transition can be made to second order. I don't fully agree with the claim because there are some things which I don't like, but anyway, let's not talk about that. But you can use non-stochastic, something called non-stochastic, which maybe if I have time, I will mention it in the later part of my talk, interactions, to kind of convert exponential scaling to a polynomial scaling and help quantum annealing. But this is not the approach which I'm going to talk about. But before I talk about my approach, what we did in our work first is to figure out how exactly and why exactly the gap closes during quantum annealing. And in doing so, we found that, sure, if a system goes to first order phase transition, typically you get a gap closing, but no, the different first order phase transitions are not equivalent. They are different kinds. In fact, there are two extreme cases of such first order transitions. Recall that the problem Hamiltonian, which is what you have at time t equal to the final time, let's say, looks like this, which is completely diagonal, which means if you forget degeneracies in your problem, your ground state on all of your eigenstates basically are going to be computational basis states. They're just going to be basis states. And if you think about it, those are like ferromagnetic states, except it's not pointing all towards the same direction, but it's just one computational state. So there are two kinds of things. One is initially, also initially I said we start with the sigma x, the local sigma x fields. That ground state, it has to be a paramagnetic ground state. It's quite obvious. Whereas on this side, you have something which is paramagnetic, means you have a superposition of all computational states. Where on the other side, you pick up one single computational state. And it so turns out that you can have a transition between those two states while you're doing quantum annealing. And this ferropara transition can be first order. Now, be very careful about this. You have a traditional 1D Ising model where it's a second order transition. For a second order transition, the idea is that all the states which I've drawn here also kind of participate a bit in the transition. But if you want to have a first order transition, which you have in the variation of the Ising model, which is called the p-spin model, you have only two or a couple more maybe, but this is the simplest version of it, only two states which are participating in transition. Okay, and the rest of them are all energetically like separated out. So you can't use them to kind of connect between these two states. And that makes, I'll talk about it in the next slide itself, and that makes this gap really, really small. So on one side, you have the paramagnetic ground state and ferromagnetic excited state. On the other side, you have a ferromagnetic ground state and a paramagnetic excited state. That's one kind. The other kind is called perturbative process, which is going to be, again, what I'm going to focus on in the most part of my talk, which is that the MWIS, it's called maximum weighted independence set. We are going to see later what that means. Now, it's, as I told you, the problem Hamiltonian will pick up one single computational basis state. But it can so happen that during your anneal, the computational basis state, which is the ground state, may flip. So let's say, I hope this is visible. So let's say there's some computational basis state here, which is the excited state, and something, this is the ground state, and they flip. The ground becomes excited and excited becomes ground. Look at it very closely. The Hamming distance between these two states, so the number of spin flips you require to connect these two states, is basically L, maximal. And when this happens, you again get a first order transition. So there are two kinds, and that's what the first identification we did in our paper, which was not clarified before. Now, why do you have such small gaps if such a thing happens? So for that, since I told you the only thing which is really relevant is a two-state problem, you can write down the two-state Hamiltonian and look at the off-diagonal term. Because if you solve this 2 cross 2 problem, you will see that the energy gap is basically 2 times the off-diagonal term. So the off-diagonal term will dictate how much the energy gap is at the critical point. Now, if you look at the two states involved here, the paramagnetic state is the superposition of all computational states, while the ferromagnetic is just one state. And this one, the only term in annealing which is quantum, is the spin flip term, which flips one spin at a time. And there are only L such candidates here, which connects to this one single computational state, which means if you do it carefully, the order of this term will be L by 2 to the L, which means that your gap at this point will be proportional to 1 by 2 to the L, which is exponential in system size. On the other hand, here you actually have this term to be exactly 0 in 0th order. So to really find out the gap, you have to go to higher and higher orders of almost degenerate perturbation theory. But each time you apply the operator sigma x, it will take you from, let's say, this state to somewhere in this space, which means each time you operate the system, you will get a denominator, which is this large energy gap. And if you have L spin flips separating this state and this state, this automatically means that you have to apply the sigma x term L minus 1 times, technically, to go from here, this state to this state. And then your denominator will be, again, something to the power L. So two different ways, but both ways you're getting an exponentially closing gap. But what this means is if you just use your sigma x driver, sure, theoretically, if you take a long enough time, then you're going to get the correct ground state. But practically, you cannot control a quantum system for a very long time. So if you use that, you're always going to get excitations and you're always going to go away from the ground state. So you have to figure out a way to mitigate this. So this brings me, okay, before going to that, let me tell you a bit about an example of such a bottleneck, which is the famous Grover search, which famous Roland Surf kind of put in the adiabatic context. So the Grover search, the problem statement is find a marked element in an unstructured database. Now, this might sound cryptic, but think about it in this way. You're trying to find a number in an unsorted list. Or if you don't like that, basically you're trying to find a word in an arbitrary book. A dictionary is like a sorted database of words, but a normal book is an unstructured database. So that's what you're trying to do. So Grover showed that classical search algorithms, I mean, classical search algorithms are order n because at the worst case scenario, you're going to find the word or the number at the end of your list. But quantum algorithms could speed it up to square root of n. And the intuition that Grover's had for this was that, okay, if I encode all of the words or all of the elements of the database into a quantum state with equal superposition of all of them, then each of them will have 1 by square root of L in front. Okay. But then it means that to figure out what is the correct solution, I can amplify the coefficient in front of it to 1 while reducing the rest to 0 in square root of L steps instead of L steps because of this 1 by square root of L factor in front. The actual algorithm is not as simple as this, but this is an intuition. And you can also have an annealing analog to this, which was discussed by Roland and Cerf. So the problem in annealing context is to find the unique ground state among n possible quantum states. Okay, and to discuss the Hamiltonian. So if you look at the problem Hamiltonian, this just means that it's an identity, and then one of the computational basis states, which can be arbitrary, to be honest, has a slightly lower value than identity. So that becomes the ground state then. On the other hand, the driver Hamiltonian here in this Grover problem is typically taken to be an all-to-all connected Hamiltonian. You might not see it immediately from here, but if you expand this psi, you will see that you are connecting all i's to all j's in the Hamiltonian. It's an all-to-all connected. But the thing is, each of them has a strength of 1 by square root of n. So this is where the 1 by square root of n comes. And if you do the maths carefully, you will see that it just boils down to a 2 cross 2 problem. And the instantaneous Hamiltonian, which is what we look at annealing, is just this kind of a Hamiltonian. It's just for showing. The good thing about this is because it's 2 cross 2, you can find out analytically what's the difference between the ground and first excited state. And you can show that it's basically, sorry, is there a question? No. Okay. So it's basically during your annealing, then it goes through kind of a gap closing point where you have the ground state and first excited come really close together, and the gap actually goes inversely proportional to system size, square root of system size, 1 by square root of n. And as I showed before, the best case scenario for annealing, which they found what is the scenario as well, the total time taken would be square root of n. So it matches with the Grover algorithm, which is completely different to the annealing algorithm. But coming back to the phase transition point, we have to figure out a better way to do it, because those unstructured problems, the Grover algorithm is the best, but most problems which we actually work with are called structured problems, which we believe to have better scaling than square root of n, which we showed before, because square root of n is quadratic. Nobody's interested in that. We want exponential. I mean, what's the other use of quantum mechanics then? And so we have to learn from classical phase transitions, because quantum phase transition is typically showing the bottleneck. So the thing is, it means that phase transition typically means there's some kind of order in one of the phases, and order implies long-range correlations in your system, right? And Ising transition, obviously, long-range correlations and order is shown. For example, the 2D Ising model, you have this domain formation near critical points, and there's order and correlations. And it is well known that if you use classical algorithms like the classical Monte Carlo, single-side Monte Carlo, Metropolis, it shows critical slowing down. Near the critical point, the algorithm takes really, really long time to reach the ground state. And to be quite honest, this is also kind of similar to classical simulated annealing. But then there were people who figured out what is the way to do that, to kind of counter that. And that the solution was cluster algorithms, where you flip large connected clusters while keeping the detailed balance intact. So this is Frentzen, Wang, and the Wolf algorithm. This was one of my inspirations to do what we did. So what can we do for quantum systems then? Can we introduce this into quantum annealing? Because clearly single spin flips are causing the problem. I showed you, because of single spin flips, you cannot connect states at the same time and everything, and the gap closes and so on and so forth. So can we do this? And this is what brings me to our approach to try to solve the problem, which is the catalyst approach to remove bottlenecks. And this sounds like a chemistry thing. I'm assuring you it's not. It's a physics thing which we are doing. But the nomenclature has a certain reason. But before we go into what is the reason, I need to tell you what the problem which we're going to focus on, the NP-complete problem which we're going to focus on. We'll be looking at these kind of graphs a lot for the next 20 minutes maybe. So it's called a weighted maximum independent set problem. Again, a very mathematical looking problem, but then you could connect it to physical things as well. So the thing is, you have a graph. A graph basically is an object which has a set of vertices and a set of edges. And each of these vertex has some weight on it. The weight is given by the numbers here. Your task is to find out the set of vertices which are not connected to each other and which has the maximum total weight. So in this graphs, for example, you can see this ones on the outside are not connected to each other, but the set which are not connected to each other and has the maximum weight is actually this set, because you add these 3, you get 9, you add this, you get 6. So this you have to find it in larger and larger graphs. So this is the maximum weight independent set problem, and this is hard classically again, which is pretty similar to the traveling salesman. It can map the traveling salesman, in fact. So what we do is, obviously we map this problem, which I'm not going to go into the details, just telling you that this problem, which is again is a mathematical object here, which you maximize a function, minimize a function. You can map it to an Ising model, which looks like this, which has, as you saw before, sigma z terms, but not like 1D. It can be arbitrarily connected. It basically, this is the graph edges, simply speaking. And then the weights on the vertices look like this. It's a bit complicated than usual because of the problem state nature itself, but this is like the weights on the vertices. And the solution to the problem is you have to find which positions or which vertices have up spins. So once you do that, you're going to find the solution to the problem. So this is what we are going to use. So now what we did is what any physicist does is try to create toy examples which are completely tractable. We don't go to the graph, in random graph initially, because you can't tackle that. You have to first create a toy problem. And this is one of few of my collaborators. We had they started this toy problem in a different context before, so we took that. And this is again the annealing style. And then you can show that, so this is called a bipartite graph, where these are like J's, which are connected. All of them are same now. And inside each partition, it's not connected. So it's a bipartite system. And the idea is this full partition has a weight, and you kind of choose two different weights, slightly different weights in the two partitions, and you divide it in between this. And the good thing about this is we can control this toy example so much that we can decide when it can show a first order phase transition during quantum annealing. And I'm not going to bore you by saying how we do it, but the idea is if you choose the difference between these two weights to be smaller than the minimum weight of the individual spins, you can show that the ground state and the first excited states are basically complete opposites of each other, meaning that if this is the this was the ground state where this was all down and this was all up, and then the first excited state would be then this one all up and this one all down. And you can show mathematically that if you can do this and under some other conditions, you're always going to cross a first order transition point when you do quantum annealing. And the reason is again because this is the perturbative transition, because you have two states which you cannot connect directly by sigma x. So it goes to higher order of perturbation. So there is no level repulsion possible. This is a different language, but I like it because I work a bit on quantum chaos as well. So for quantum chaos language, it's called no level repulsion possible. Okay, so this model, we have this model. So what do we do? So this is where I'm telling you what the catalyst is. So we call it a catalyst because we kind of put it to enforce it to be 0 in the initial and the final stages of the annealing. So it begins at 0. So if you take s equal to 0, this term is 0. If you take s equal to 1, this term is 0. So that You do not sacrifice the ease of preparation of the initial state, and you do not sacrifice the solution. Of course, you cannot sacrifice the solution. And the question then remains is how to choose the catalyst, and that is hard. And we do not have a foolproof solution yet. We are working towards it. But theoretically, as a theoretician, you can easily say one thing. If you could connect directly the almost degenerate states involved in the first order transition, meaning if you could make that off-diagonal element here to be large enough, then you're going to open up the gap. The crucial thing which one should realize is, you remember there has to be long range order present because this is a transition, which means if your catalyst is completely local, it cannot work for a general scenario. It has to be n-local or non-local catalyst. So it has to be a non-local catalyst to cause level repulsion to open up a gap. And typically, smaller the gap, the bigger the non-locality required. So this is the thing. So what we consider in our work is a couple of cases. So we take this bipartite system. This is the standard system, which is the vanilla annealing, which has just the X driver. Now you can use these edges to add another term here, which is the XX. Instead of just X, now we have XX plus X in now here. And now we are showing two colors because these edges now have sigma X, and sigma Z, sigma Z. So now it has two colors. So this is one thing which you can do. The other thing which you can do is you can use an all spin flip term, which means that this is a pi means a product of all sigma X, which is there. So for graph theory people, if there's anybody here, this is like a hypergraph in a way. So this is still a graph, normal graph. This is a hypergraph because you're connecting several vertices at the same time. And this is physically motivated, and this will give you the solution, I can already tell you, is because the two states which are involved in the transition are all spin flip versions of each other. So now this will connect those two together. This is called a direct coupling or direct tunneling catalyst, and it's going to work. But this, we have to see whether how much this works as well. And so for the results, so if you do compare these three cases, let's say the blue one is the vanilla annealing, where this is the gap during your anneal, and this is kind of the renormalized annealing time. You can see the gap is like very small, 10 to the minus 6 or something like that for the vanilla annealing. If you use the XX catalyst, it increases. While if you use the product catalyst, there is no transition at all. And it just verifies your theory, which you would anticipate. You can, since this is a transition, and you have to find an order parameter, and the best order parameter here is the imbalance between the two partitions. And you can show that the imbalance suddenly changes if you have no catalyst, which is the hallmark of first order transition. And if you use an XX, it's still sudden, but it's weakened, right? You don't remove the transition, you just weaken the transition. But if you use the product catalyst, there is really no transition at all. It's a complete crossover. So this is the idea. But this was a toy model, right? So the question is, how do we do it if you don't have toy model, if you don't have a perfect scenario? And that is the hard part. For a general model, you will not have the structure priori, and hence the specific catalyst which worked really well here is not going to work everywhere. So we have to rely on imperfect catalysts at the moment because we don't know how to do it without actually completely solving the problem. The question is, how do we select the sites we put it on? And this is something we answered for the MWIS problem in our work, and I'm not going to go through the mathematical details. But what I'm showing here are basically subgraphs, kind of, from a full graph. So if you have a very complicated, imagine a very complicated graph, if you break it down, you're going to have subgraphs which look like this. So this is like a so what I'm saying is you should add a catalyst here. So this will be like a 2-point catalyst, XX. This will be like a 3-point catalyst, XXX. Then this is 4, and so on and so forth. So what we found is that if you have these kinds of structures, which is like even and or regular and so on and so forth, or not frustrated is a physical term, then you should add catalyst there in a hierarchical manner to get more improvement. Okay, so you start with XX, and then you see whether you get improvement or not. Then you add XXX if you see if there is improvement in your solution, and so on and so forth. And you stop when, depending on the limitation of your hardware or limitation of time, whatever you want to do. Whereas if you have these kinds of structures, triangles and frustrated squares and pentagons and so on, you should not add catalysts to that. And we have, there's a mathematical reason behind it, because you can show that if you have frustrated structures, then the all spin flip terms around this frustration is never near the ground state. It's very far away. But let's skip that. It's a bit of math. So if you're not understanding what's going on there, I can show you this graph. For example, what I'm trying to say is in this graph, you should add catalysts in the greenish regions, while you should not add catalysts in the red or the orange parts. That's what I'm saying. So this means that I should add an XXX here, but I should not add an XXX here. That's the entire point. And we've found out an example where, again, we could generate a transition in this random graph. And we could show that the catalyst, if we add this XX catalyst, so again, these are three cases: no catalyst, transition, XX. If you add XX, then you improve it a bit. And then if you add the next one, the XXX, you kind of remove the transition completely. But of course, you will argue that, okay, but this is just one example. What are we doing here? Well, we also did many other examples. And we did it for two classes of graphs. There are actually graphs can be divided into a lot of classes. And these are kind of two classes of graphs, depending on the distribution, the degree distribution of the degree means how many edges does a vertex get connected to. The degree distribution for a Gaussian graphs is kind of like a Gaussian. But the degree distribution of the Barabasi-Albert graph is like a power law. So interestingly enough, this was kind of found out in the context of World Wide Web, the Barabasi-Albert graph. And these two degree distributions have different, completely different looking graphs if you go to really, really large graphs. And we try to use our XX couplings here and see whether it improves or not. And the crucial thing to note is the y-axis is the catalyzed catalyzed gap, and the x-axis is the uncatalyzed gap. And this line shows when both of them are equal. So anything above this line is good for us. And we generated thousands, 10,000 instances from the Ardash running graphs with some different probabilities. And we found that most of the cases, the catalyst improves the condition. There are reasons why sometimes it doesn't improve, but let's not go into that. I don't have much time. And same thing happens for Barabasi-Albert graph for 10,000 kind of considerations. And even if he takes different system sizes, I'm not going to claim that it improves with system size. I'm going to just claim that it's going to be like, it's kind of constant with system size. So this is a geometric mean, and there are reasons why we choose geometric more than arithmetic and so on and so forth. And again, more statistics in random graphs, you can show that this was just XX, right? So here, the C1 shows XX and C2 shows if we go to the next step, XXX. So visually, you can see that, again, everything has to be above this line to be good. And you can see that if you go from XX to XXX, points start to move upwards. And if you're not convinced by these two graphs, then this is XXX versus XX. So again, the XX, the fact that the three local catalyst is better will indicate that everything is above this line. And that's what we are shown here. So the proposal is hierarchical addition of n local catalysts that improvement is seen or system limits are reached. Okay, so I guess I have 10 minutes more, so I can talk about the gate-based implementation of what we are doing. So technically, we can do whatever I was saying in gates as well. It's just that you have to decompose it in universal gates, and then if you want an XXX gate, you just have to use ladders of C0s across an Rx. That's basically it. And we also showed these results for, this is again numerical simulation for gate-based annealing. What we're showing here is if you take the trotter steps, the number of trotter steps you require to reach a good fidelity in the solution is improved exponentially, basically, or orders of magnitude if you want to be precise, if you use this catalyst. In fact, if you use this catalyst, it really shows how it is. And if you count the gates, because if you're adding the XXX and other catalyst terms, you're actually increasing the number of gates in a single trotter step as well. But even if you count that, it will still see that you can get a higher fidelity with an order of magnitude reduction in gates if you add catalysts. So this is kind of the gate-based version of the continuous version of what we showed before. I think I'm going to skip the non-stochasticity part of this, but the main thing is that in our scenario, non-stochasticity basically means the catalyst is an opposite sign to the driver. And the gist of the matter, which I'm trying to show here, is if we do that in our model, contrary to many, many annealing beliefs, this does not help in our problems. And we found out why. The reason why is because this is, as I showed you in the beginning, this is a different class of first order phase transition to what the original non-stochastic catalyst which Nishimori and others did, which was in p-spin model, which was the first kind of transition. There you can show the non-stochastic catalyst works and it improves, whereas in our scenario, which is like the perturbative crossings, it doesn't improve. So that's why we needed to differentiate between the two classes of first order phase transition to show why in our model things are different from what people believed before. Okay, so now I've been telling you that gap closing and everything is really, really bad. But while doing the quantum annealing problem, I noticed something very interesting is that gap closing might be good for quantum sensing. And this is local quantum sensing because of certain mathematical things about Fidelity susceptibility and quantum Fisher information, which I don't want to go into it. But the thing is, if you are across a transition, you have an order parameter which is an optimal observable already. So that you have a ready-made observable. If you have an observable which really changes exponentially fast across a transition, and that gives you sensitivity. And we used several models and this toy model as well to show that the Fisher information, which is kind of the quantifier of how good your quantum sensor is theoretically, with system size, it grows exponentially. And even if you take the state preparation time into account, it still grows exponentially. And we showed it both analytically and numerically as well. And this was a very nice idea which got published last year in Nature Communication. We are trying to now kind of advance it, but this is something which is bad for one particular aspect of quantum technologies may not be bad for everything. It's good for something else. So yeah, this was quite a fun project. So moving on, let me give you a glimpse of a bit of quantum hardware data in the last 5 minutes. So as you saw that in D-Wave, you don't have XX coupling. I'm telling you, you need XX coupling and you don't have XX coupling in D-Wave. So what are you going to do? So that's why we have designed some gadgets. So this is the first gadget we are designing, which is the trust gadget. So I can't tell you in details how the gadget works because it's a patent in progress, but I can show you that you can design gadgets which uses the X couplings to generate an XX coupling in a quantum annealer. And so we tested it on a simple 5-spin model, which is periodic. So what we tried to do is we tried to have a Hamiltonian which has XX couplings and ZZ couplings and Z, and tried to simulate it with our gadget, which uses only X couplings. We simulated it on a gate-based computer because we wanted to do a quantum quench, which is not very easy to do on D-Wave. So this is an ion trap, ion cube computer. And what I'm showing here is the probability, the evolution of one single computational basis state, how it works out. So we started off with the paramagnetic state again. And you can see that the continuous Schrodinger evolution, which is theoretical, matches quite well with the data, I mean, with errors, of course, because we had limited shots of quantum computers. So our thing works actually in a quantum computer. So this is something which we did. And the other thing which I really want to emphasize is I believe, and even now Google believes, that neutral atom computing is probably one of the best solutions in near term and not superconducting qubits at the moment, because it's so versatile. And in this paper, what we did was we kind of could actually control where we place the atoms like a real experimentalist, and then do some driving of the terms in the Hamiltonian, and then see actual interference patterns like bright and dark fringes. So these are dark fringes and these are bright fringes, and showed something called dynamical localization, which is a many-body quantum phenomenon technically. And it was beautiful to see, and the degree of, and this is like the theoretical line, a numerical line, and this is the kind of experimental line, and they quite agree enough for me, because the sizes are also really different. So this is really nice. So this brings me to the last slide, which is what's next. So I want you to take back 3 lessons from this entire talk. So first thing is that some of the gap closing during annealing is a shortcoming of the traditional annealing protocol, right? That's what I'm trying to tell you. If you're using just sigma X, it's a problem of that. And then direct tunneling catalyst, which connects the 2 states involved in a transition, is the ideal solution. But of course, you can't do it. You don't know what it is for a random geometry. So you have to modify the protocol multi-qubit N local catalyst. And I believe that is one of the necessary ways to convert this. And in fact, there are other techniques like the counter-diabatic protocol, which are effectively also doing this in a different way. So these connect states with large Hamming distances across the gap closing phase transitions. So what am I interested in now? So one thing I'm obviously interested in, and I think I should have something out by the next month, is what happens to quantum entanglement during anneal. So if you look at the ground state entanglement, what is it? So the one spoiler is gap closing does not really mean high entanglement or high bipartite entanglement. It means that the entanglement structure is quite interesting, but it does not mean the amount of entanglement is high. And then, as I was just saying, the shortcuts to adiabaticity. So if I use QA-OA with this understanding, does it lead to further speedups? We hope it to be tested in some quantum hardware, maybe IBM-Q or Quantinuum. We'll see how funding goes. And one of the things which is a long-term kind of plan is to understand quantum problem complexity for this MWIS instance. So there are quantum complexity classes like classical complexity classes. I want to see what kind of problems are hard for quantum and classical, or if the problems for classical are not hard for quantum, like what is kind of the overlap. I don't think for, at least for this class of problems, it's well understood. And of course, the biggest problem which we face today, and this is kind of quantum algorithms is the thing which is we require the most in today's world, is practical implementation. Can you design a coupler based on some pre-processing, post-processing of results? What is the proof of principle in a thermodynamic limit? And can we figure out the edges by using some Monte Carlo sampling and so on and so forth? So lots of questions, and this is a very interesting area to be working on now. So, and these are all my collaborators, and all of them really I worked with me at UCL, but now are at various places. Luca has gone on to Oxford, so these people are all already in UCL. So Sebastian is our kind of D-Wave helper guy who's in Jülich, who has a D-Wave machine. So he kind of helps us simulations in D-Wave, but unfortunately I could not show because it's protected by some laws, so I cannot show you. And yeah, so Ben is the one works on a lot of quantum hardware like gate-based and everything. And Bhaskar and Madhumita are, Bhaskar is now a professor in Hyderabad, and Madhumita is the postdoc in UCL. So thank you for your attention, and thank you for the opportunity again to speak. Yeah, these are basically kind of the papers which I covered in the talk.
Okay, let's thank Professor Ghosh for an excellent exposition to the subject, and now it is open for questions.
I have two questions. Thank you for a very interesting and informative talk. If you introduce dissipation in your calculations, what kind of changes you may expect compared to non-dissipation case?
That's a very interesting question, because D-Wave annealers actually have dissipation in itself, because it's known to be coherent for only 30 nanosecond, and people do computations in microseconds there. Now, the interesting part is sometimes dissipations can be really helpful, because it helps you to also traverse the landscape classically, right? Because you're introducing heating, so somehow some barriers you can traverse classically. So sometimes it kind of helps you to get to the solution faster in a way, because ultimately you're solving a classical problem. So you don't really care about quantum superposition in the end for such solutions. However, I would also be very cautious about this, because there have been papers which are trying to figure out what is the exact mode of dissipation that is actually helpful, because that we don't know yet. So it's kind of like a black box. So you will see some results from people working on D-Wave showing, oh, we have got such a good result for this problem. We do it faster than classical mechanics and so on and so forth. But we always take it with a pinch of salt, because at the end of the day, D-Wave sometimes behaves like a huge classical annealer with dissipation inbuilt, and dissipation actually helps in this way. But nobody has modeled the dissipation to figure out what exactly is the part which helps, and is there some part which actually slows down and we can speed it up faster.
So does it mean that your simulations are carried out in D-Wave machine?
No, my simulations are completely in ideal like classical computers. I always did classical computing simulation. So the time scales which we require to actually simulate in D-Wave is what we don't have. And so we don't bother, because it'll become classical anyway.
Yeah. Let me refine my question. My question was related with the search algorithm, because if you introduce dissipation, and then you will have some impacts on your matrices which you obtain in case of non-dissipation case.
Absolutely.
Okay. My final question, could you name the software packages used by you for simulation on classical computers?
Oh, so I usually do Mathematica and Python, but I write my own Hamiltonian codes and stuff. But however, if you really want to like do this gates-based simulation, for example, where I showed this IonQ result. So even that you need to simulate first classically and then put it into a quantum computer. There I use the AWS Bracket software. So that is I think it's quite natural for us. In fact, there are loads of softwares. I think CIRQ is one software. Then IBM has their own. I've forgotten what's the name of it. but I use the AWS. Yes.
Amazon, right? This is
Amazon
Amazon.
AWS. Exactly. Yeah.
Okay.
Yeah.
Thank you. Thank you.
Yeah, I have a couple of questions. Pijus.
Yes,
Yeah.
go ahead.
Yeah, I see. In past order phase transition, we know that defects can help you in going from one phase to the other because defects usually manifest in past order phase transition and they combine to drive you from one phase to another. Are you using this, your sigma x to create something like a correlated defect?
You can technically argue. So how I look at it is by using the sigma x, I'm trying. So I can connect in nth order of perturbation if I don't use it. So by sigma x, at the best case scenario, you're going to connect it at n/2 order, right? The worst case scenario. But sometimes the landscape, because it's a structured problem, the eigenvalue landscape can be such that some eigenvalues are not participating in the obviously the transition, but are really close, right? So somehow you can connect there, and if you connect there, then you can pull the gap apart, right?
Correct.
That's exactly what I'm doing.
Yeah. Why I asked specifically is because sigma x cross sigma x really creates Bell state out of product states.
I guess that is correct. I have to entangle the correct states after all. I mean, that is so that is kind of the paper which I'm writing to show that it's not about the amount of entanglement. It's about entangling the correct spins and then pulling it apart.
Yeah, very nice. Other thing you said that Fisher information goes like exponential.
Yeah.
Does that mean that like in first or second order or first order phase transition, these correlation domains could diverge? Is it reflecting that these critical fluctuations, those kind of things?
Actually, interesting. So the correlation domains usually diverge in the second order transition, right? So therefore, but Fisher information does not go exponential. It goes polynomial there. Only in first order it goes exponential, and because in the Fisher information, which is you will have in the denominator the energy. That's what comes in Fisher information. The energy gap between the ground and excited. So that's what blows it up to e to the power L. So that's what we used.
Yeah, very nice result. Really enjoyed. Thanks. Yeah.
Thank you.
Okay, any other question? No? Okay, so let me ask one thing that first is that graph theory or this network plays a very important role, if I understand correctly.
Yeah.
So you see that, so are there any universality or similar sort of results for isomorphic graphs, or it's dependent on the specific type of graphs?
This is something which I want to do eventually. That is one of my things. As far as I'm aware of, there are no results. So what the thing which people have understood is if you have a tree-based graphs, things become very easy. Like if the graphs are like trees, it's classically easy and also quantum mechanically easy for some reason. But if you have loops, like triangular loops like in the graphs, it becomes very hard. That's what people know. But nobody has, for example, this Ardha-Shreni, nobody really knows that for a class of Ardha-Shreni graphs, what should be kind of the local fields of the structure to really say, okay, this is the hard part of it. We'd have to do it differently and so on. There is no result. And this is something which is a long-term goal of mine to figure out. And I'm hoping to use quantum annealers like D-Wave, even if it's not quantum, because you can like embed huge graphs there and see what happens, right? You can't do it in the classical computer. You can do it there. So that's something really which is, I think, which we should do to really understand what's going on.
And the second part is that during the last part of your talk, you mentioned about you observed dynamic localization.
Yes.
Page 44 or something like that.
Yeah, I can
if
share.
There is a dynamic localization, so I should expect that there will be local integral submotions.
Absolutely.
Okay, so does it accelerate or prevent the minimization?
So, okay, let me just say that the dynamical localization was just to show some results. It's not really connected to annealing. So it was, I just wanted to show some hardware results. But so the thing with this dynamical localization is what I don't understand fully is adiabatic. I'm very comfortable with it because I know the solution will arrive because it's adiabatic theorem guarantees it. But this, if I use dynamical localization, then I'm going to use a non-adiabatic procedure. And I am not convinced that I'm always going to get the solution. I mean, I'm sure there are theorems which prove it. So I don't use it there. But about the dynamical localization, there is local integrals of motion. In fact, if you write down the effective Hamiltonian, you will find that you kind of conserve the sigma z operator in a way. Like it drops out of the first two orders of perturbation, and that's why it's conserved. And the main thing about that work was it was the first work which shows what happens if you really have interactions with dynamical localization. Because previously, that most of the theoretical works were using Ising models, which were not really, I mean, it's not interacting. But if you have interactions, we showed that you're still okay, but there is some things which becomes worse. So that's kind of the work which was there. And
yeah, I would expect that it will. I mean, it will not be an advantage, but disadvantage.
Yes, but interestingly enough, for some initial states, you get new frequencies where you get dynamical localization if you use interaction. And we couldn't do that experimentally yet because preparing initial states in an analog is just a mess. But that is something we don't understand, and that is we hope to understand in this year. But so what I'm saying is it's not always a disadvantage, or maybe once we understand more, we'll figure out it's for some other reason. But right now, that is my opinion on that.
What about one? I will go one more level up. Quantum chaos, any signature, and if it is there, then how do you handle it?
So interestingly enough, there were peaks and dips, right? So the dips were dynamical localization, the peaks were quantum chaos kind of thing. So in some frequencies, you get quantum chaos really early. So at the end of the day, you will get quantum chaos.
So how do you verify that? Level statistics or some other?
Oh, so here experimentally we don't verify quantum chaos. So in fact, there is a science paper by the van der Sijpen's group which actually calculated level statistics in quantum many-body system experimentally and showed quantum chaos. So that's like very recent. It's not even available commercially. So we don't do that. We just believe that it loses the memory of the initial state. So it's quantum chaos. It's not precise, but that's pretty much the definition which we are kind of using.
Okay.